This is a quick video on what is sometimes called atomic weight, although as it proves, that's a horrible thing to call what we're going to talk about in this video. And by the way, I'm following the order of Brown, LeMay, Burston, and Murphy's Chemistry, the Central Science. Okay, what is this thing called atomic weight that really shouldn't be called that? Well, you might remember from a previous video that the unit of mass for the atomic world is the AMU, or the atomic mass unit. Now we can tell you exactly where that comes from. So it's based on carbon-12. So in my previous video I talked about different isotopes. Different isotopes of an atom are basically, they're the same atom, because the same element, that is, because they have the same number of protons. It's the number of protons in the nucleus that tells you what atom it is, what element it is. So carbon always has 6 protons. If it had a different number of protons, it wouldn't be carbon. However, carbon has several isotopes, at least 3 isotopes that I know of: carbon-12, carbon-13, carbon-14. All of these isotopes have different numbers of protons, neutrons, that is, in the nucleus. So carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons, and carbon-14 has 6 protons and 8 neutrons. So basically, if you take the mass of carbon-12 and divide by 12, that gives you 1 atomic mass unit. So carbon-12 is the isotope of carbon that has 6 protons and 6 neutrons, and if you divide the mass of carbon-12 by 12, that gives you what an AMU is, what the atomic mass unit is, which proves to be about, this is approximate, 1.66 times 10 to the negative 24th gram, which is really small. So what is the average atomic mass? Now this is what is sometimes called the atomic weight. If you've had physics, you know why this is a horrible thing to call it. The difference between mass and weight is, weight in physics is the mass under gravitational pull. We really don't want to talk about the mass of an atom under gravitational pull. That makes very little sense whatsoever. And so it's been called atomic weight forever, and so we continue to call it atomic weight. But what we're really talking about is the average atomic mass of an element or a molecule. So what is that? Well, basically, if you take the masses of the different isotopes of an element, so carbon-12 is by far overwhelmingly the isotope of carbon that's found in nature. Carbon-13, only a little more than 1% of all the carbon in the world is carbon-13, and even less of the carbon in the world is carbon-14. And so you take the masses of the 12, 13, 14 isotopes, you take the masses of the isotopes of an element, you multiply it by their relative abundances, and then bam, you have, when you add those together, you have the average atomic mass, or what is sometimes horribly called the atomic weight. So basically, here's an example. So 98.93% of the carbon in the world is carbon-12. So if you multiply 12 by 0.98%, you get basically 11. Carbon-13 is the next most plenteous isotope, with 7 neutrons in the nucleus. Only 1.07% of the carbon in the world is carbon-13, which if you multiply 13 by 0.01, you get something like 0.13, 0.14. Okay, so basically if you take these and add them together, you get 12.01, which if you look in your periodic chart, at the very bottom in the periodic chart, this is Brown, LeMay, and so forth, Burston, Murphy, this number underneath is the atomic weight. It is the average of the atomic masses of the isotopes of whatever element you're looking at. And so no one atom is going to have this particular mass. This is an average of the masses of the different isotopes of the element by how abundant they are. Okay, so that's what atomic weight is, badly called. There's also a little section at the end of this section on mass spectrometers. Mass spectrometers, it's an instrument that's used to try to determine the various elements and masses of the elements. So a magnetic field is used to deflect atoms according to their masses. So you might take chlorine and ionize it, and then the magnetic field will take the various isotopes of chlorine, and they'll hit different spots. So you can actually tell the difference between the different isotopes of an element when you put it in a mass spectrometer, because the mass is going to be just a little bit different. So the mass spectrometer helps us identify the elements that are in something. So you could take a substance and use the mass spec and figure out exactly what elements and isotopes are in that. Well, this is a very quick video on atomic weight, badly so called.